And our next speaker will be Jesun Firoz from Pacific Northwest National Labs with a talk titled Computing Hypergraph Homology in Chapel. And as I just said that, it's 12:30 and time to start. So Jesun, you can take it away.
Yeah. Thanks again. Hi, everyone. My name is Jesun Firoz. I'm from Pacific Northwest National Lab, and today I'm going to present our work titled Computing Hypergraph Homology in Chapel. So the outline of my talk is going to be, first I'm going to talk a little bit about what hypergraph means, and then I will talk about what hypergraph homology computation means and what's the motivation of doing this work. And then I will briefly talk about a little bit of a comparison between implementing linear algebra operations in Chapel versus Python. And then I will go a little bit details about how we implemented our hypergraph homology computation in Chapel. So there are two main steps there that I will discuss, and then what are the optimizations we did, and I will briefly discuss about our experimental results. So most of us probably know about graphs. So graphs are very good in terms of doing these mathematical abstractions where we want to model the interaction between different entities so that different questions about connectivities, reachabilities, or density or clustering, these kind of things can be answered. So for example, here we have an example. For example, Bob wrote a paper with Anne, and Anne wrote a paper with Carl, or Bob wrote a paper with Carl. So that's pretty much very easily modeled in terms of graph. But what about a paper that has been written by three person, Bob, Diane, and Carl? So this kind of modeling in terms of graph is a little bit challenging. So it requires higher encoding strategies, for example, in terms of property graphs and assuming bipartite structures, reification, and so on and so forth. So here comes in hypergraphs to basically model these multi-dimensional graphs. So what hypergraphs are here are basically hypergraphs consist of vertices and hyperedges. And hyperedges means that one hyperedge can contain multiple vertices. And that's the advantage that we can basically leverage to, for example, model the previous example that I was mentioning earlier, where if Bob, Dan, and Carl wrote a paper, then we can basically say, hey, all these vertices, which represent these entities, Bob, Dan, and Carl, can be represented as vertices, and then they can be connected with this hyper edge. So this is the motivation of using hypergraphs. So the next slide here, what we are showing here is that hypergraphs, since they are multidimensional objects, they have some topological properties. So these hypergraphs can be hollow or void, or there can be solid inside them. So for example, here we are showing a hypergraph where there is a hollow, one-dimensional hollow hole there, and then there can be another hypergraph where there is a solid there is a solid entity there, but inside that solid there can be a hollow, so that can be a two-dimensional hole. So and so on and so forth. So what we are interested here is that we, given a data set, we want to find out, we first model these data in terms of hypergraphs, and then we are interested in finding out, okay, if this data is represented as a hypergraph, is there any hole there, and is there any one-dimensional holes or two-dimensional holes or three-dimensional holes, and what are the associated data there, or what are the metadata that's in there that can be correlated somehow. So these we are so in this talk we are basically going to find out these beta values. So beta 0, beta 1, beta 2, these basically means I have one hole for this structure, one zero-dimensional hole in this structure, one-dimensional hole in this structure, and zero two-dimensional hole in this structure, and so on and so forth. So this slide is kind of giving bird's eye view about this different linear algebra operation that goes on. So I'm not going to go into details. The idea here is that there are different linear algebra operations that goes on to compute this hypergraph homology. But ultimately, we can assume that, let's assume that we are given these this matrix. So what hypergraph homology does, it computes the difference between the kernel of this matrix, which we call a boundary matrix, and the difference between these, the kernel of this boundary matrix and the image of this boundary matrix in k dimension. So so the dimensionality actually matters. So ultimately what we are showing here is that there are different, there is these boundary matrices that we will compute, and then based on these boundary matrices we will compute a particular representation of that boundary matrix, and then we will compute these linear algebra properties, for example rank, kernel, and dimension, and so on and so forth, and which ultimately will give us some kind of number or value, which we call Betti numbers, which basically represents how many holes we have in different dimensions. So dimension can be like 0 dimension, 1 dimension, or 2 dimension, or higher, more than that. So the motivation of doing this work is that we want to learn about this missing data and the surrounding data set, but the data set can be huge, and later on we will talk about abstract simplicial complexes, and these abstract simplicial complexes can be huge. So since there is a memory requirement there, so ultimately we want to go into a parallel and distributed execution in terms of leveraging the computation and the communication capability of distributed computing. So that's why we want to leverage Chapel's parallel and distributed execution capability. And in doing this work, there are two main steps. One is, as I was preluding earlier, is this computation of these boundary matrices. And then the second step is to compute the Smith normal form of these boundary matrices, which will ultimately give us these values, the Betti numbers that we are interested in. And all these operations heavily involve matrix and linear algebra operations. So in our work, the matrices are represented as a 2D dense arrays in Chapel, and there are different array-centric operations that needs to be done. And here is some kind of a set of lists here. So we needed to do row and column interchanges, then pivot calculation, addition of rows and columns, rank computation, multiplication, slicing. And all these operations can be done in Chapel very easily, and that's one of the slides coming forward. And as I was saying, as I will show, that they are very concise and very intuitive compared to Python. And one thing I need to mention is that while there's a linear algebra library in Chapel on matrices to do singular value decomposition or LU decomposition, all our operations are in Z2 field. So that means all our entries in our matrices are going to be 0 and 1, and the operations, for example, any kind of matrix multiplication or addition operations, these are going to result in 0 and 1 operations. So that's why we wrote our own implementation for these functions. So here's an snippet between how different linear algebra operations in Chapel versus Python looks like. And as you can see, like swapping rows, addition of rows, and calculate rank, all these operations are very concise in Chapel compared to Python. And in addition to that, we are getting, for example, with for calculating the rank, if we express this reduction content, we very easily and very concisely are getting the parallel execution capability. So that's very nice. And then if we compare how would one implement a matrix multiplication operation in the Z2 field, that's also very concise and easy. And just by sticking into a for all operation, basically we are getting a parallel matrix multiplication in Chapel without much effort. And this is very nice. And in comparison to the code snippet that I'm showing here for Python, NumPy, that's basically a sequential execution. So going forward, I'm going to talk about how we implemented our homology computation in Chapel. So I'm going to give a small example to explain things more easily, and that's why I just wanted to have one slide where I'm just going to tell about one example. So let's assume that we are given a hypergraph with only one hyper edge, which contains 4 vertices. So the vertices are 0, 1, 2, and 3. So what we want to do is like we want to generate the power set of this hyper edge, and we want to bind them together or with respect of the size uh, of the cell. So we are calling these as cells. So for example, we are showing here that 0, 1, 2, and 3 are 0 cells, and then 0, 1 is 1 cell, 0, 2 is 2 cells, and so on and so forth. And we also need them to be sorted in a particular order. So here we are going with the lexicographic or numeric order. And once we group these cells together, then what we want to do is that we want to compute the boundary maps. So what the boundary maps represent is that we can assume that each, like for example, for the first example here, each row represents the 0 cells, and each columns represents the 1 cells. So the entries in each of the matrix, each of the entries of the first matrix is 1 whenever there is an overlap between any element in 0 cell and 1 cell. So they don't have to be not necessarily contiguous. So for example, 0 is contained in 0, 0, 1 cell, right? So that means we have an entry in the 1, 1 position. So we will basically compute this bunch of boundary maps. And so how do we do it? So to compute these, we call them abstract simplicial complex, but it's a fancy name of saying that we are generating these power sets. And to do that, we are maintaining one set per task per local for gathering these abstract simplicial complex. And then for each of the hyper edge, we are basically going to generate this power set in parallel. And this is happening here. So this is the code snippet that does that. And once we have this executed, then in each of the local for each of the tasks, we will get a set of cells. So in the next step, what we want to do is like we want to basically bring them together and then sort them. So that's what is happening here. So to do that, first we basically create a domain which contains all the cells, and this is hashed on the locals. So once we have this, then we try to do, so we maintain a map on one local, which tries to basically bin all these cells from different locals. And the problem is that here, since we don't have a distributed map, this merge is happening on one local. But once we have that, and then what we want to do is like we want to sort each of the cells, and that's happening here. So what for each of the cell we basically for each of the groupings of cells, we want to sort them so that they are in a particular lexicographic order. And the reason we want to do that, because we want to have a fixed ordering when we are creating the boundary matrix, so we know that which cell corresponds to which entries. And we have a comparator for doing a specialist comparator for doing that. And once we do that, so far this is what we have done. Given this a hypergraph with one hyper edge, we basically generate the power set of this hyper edge. We get all these different length cells, we group them together, we sort them, and then the next step is to generate the boundary matrix. So to generate the boundary matrix, the structure, the representation that we have currently. So here I'm showing that is integer 2D integer array, but later on for optimization we also have a Boolean representation for this boundary matrix, and this boundary matrix is a block distributed 2D array. And just to recap, this is at the bottom of the slide, you can see like this is what we are computing here. So for what we do is like for each of the boundary map, so for each of the boundary maps are computed in parallel, and for each of the boundary maps, for each of the columns are also computed in parallel. And we will have an entry of 1 whenever there is an overlap between, for example, like the cell the cell that is currently considered as, for example, 0 cell and K cell. So if there is a overlap between the elements between 0 cell and 1 cell, that means we will have an entry in that particular entry for this matrix. So so far, this is what we have done. Given the beans, we generated the cells, and then we computed the boundary maps. So once we generate the boundary maps, the next step is that we want to we want to compute a Smith normal form for each of these boundary maps, and that Smith normal form is beneficial to compute these Betti numbers, which will basically designate the number of holes that we have. And to compute these Smith normal forms, we are going to leverage the linear algebra operations that I was alluding earlier. So we basically use these operations: swap rows, swap columns, add rows, add to rows, add to columns. So these set of functions. And as you can see, like in Chapel, they're very very concise. I mean, we don't have to go element wise. I mean, the notations and everything are very easy to follow and implement. And then for the matrix multiplication, this is the same thing that I have shown earlier, except that it's just a little bit explanation about what's happening here. So for each entry in the results matrix is computed in parallel, and the reduction intent here is doing partial multiplication in parallel and then combining the partial sums. And all these are very concise. So with all these, linear algebra operations in our hand, with the Chapel implementation, what we are trying to do is that we are trying to find out the Smith normal form. So given this boundary matrix B, we want to find this form L times B times R equals to S. So this is the code here. And what I'm going to show here is that in different parts of the code, we are leveraging this swapping of rows and columns, adding to rows and columns. And once we have these, then ultimately we get back these five matrix: L, R, S, L inverse F, and R inverse F. And L inverse F and R inverse F contains all the different matrix transformation that's happening here, so that later on we can um, you can consider this as, let's assume that we are doing some set of um, uh, some transformations in the matrix. So L inverse F and R inverse Fs are basically a list of those matrices or matrix which represent these transformations. And later on, we will basically multiply this list of matrices together to find something that will be useful to compute our Betti numbers. So the potential bottleneck here is kind of inherent in the in the algorithm that based on the dimensionality, it has to be executed sequentially. So the opportunity for parallelization here is that we can compute this Smith normal form for each of the boundary matrices in parallel. And interesting case would be, how can we multiply a list of matrices in parallel? But there are other, other options too, which I will talk about a little bit later. So and in our profiling result, matrix multiplication seems to be a particular bottleneck. And one thing that kind of surprised us is that for the sequential execution for one particular computation took 25 seconds versus distributed memory 2D version took almost 2400 seconds. So we still have to look into that and figure out what's the problem there. So we did some of the algorithmic optimizations. So one optimization was that, okay, we are doing a lot of matrix multiplication. So is there a way to reformulate the algorithm so that we can somehow eliminate these eliminate this matrix multiplication altogether? And that's what we did as the first optimization. So we reformulated the algorithm in such a way that there is no need for doing a multiplication for a list of matrices. And then the second optimization we did is that since there is our matrices only contains 0 and 1, there is no point of maintaining integer operations. So we converted them to Booleans. And if we do that, accordingly, some of the matrix operations obviously is going to change. Like, for example, add to row operations on Boolean matrix is basically element-wise XOR. So that set of changes also has been done in the code. With all these changes, we did some experimental experiments. And we compared the platform that we have is a single compute node with 20 core Intel Xeon processor and 132 gigabytes of memory. And we implemented our algorithm in Chapel version 1.20, and we compared our homology package, homology implementation with two other packages. One is Perseus, which is written in C++, and another one is Irene, written in Julia. And here the legends show that CHGL means with explicit matrix multiplication was the performance, versus if we don't have explicit matrix multiplication and with a Boolean data type. So with explicit matrix multiplication, the performance was not very promising, just because we are doing a lot of matrix multiplication, and that was the potential bottleneck. So as we eliminated that, our performance improved significantly, and then going from that to Boolean data type improved even more. And we are kindly investigating more like how we can basically get on par with Perseus, which is implemented in C++. So right now our implementation the performance of our implementation falls in between you know, Perseus and Irene, but we want to be on par with Perseus. So in conclusion, we implemented a parallel and distributed version of homology computation in CHGL, or Chapel Hypergraph Library, if you don't know about it. And to do that, we implemented the computation of the boundary matrices, and we implemented the computation of the Smith normal form and computation of the reduced row echelon form, which has not been shown here. And our, our experience shows that the linear algebra operations are very concise, intuitive, parallel, and distributed, obviously in Chapel. The main bottlenecks that we found out is that in terms of overhead of shared memory versus block distributed memory, that's one of the bottleneck that we need to address. And matrix multiplication was one of the time-consuming kernel. And moving forward, we want to find out a better scalable and distributed implementation that goes on par with Irene. So with that, I would like to thank you for attending the talk. And if you have any question, I will try my best to answer that. Thank you.
Thanks a lot. Great work.
Thanks.
There's one question in the Q&A box from Brian Dolan. He says, do you intend to release your Z2 linear algebra module as a separate open source code base?
We can definitely think about it. They're very, they should not be very hard to do. So that's a great suggestion. We will definitely try to do that. By the way, I should mention that everything we have here is on the on our GitHub repository. I forgot to include the link, but everything is currently open source, except that the linear algebra module, the J2 linear algebra module, is not, it's this basically ingrained into the code. It's not part of it or different.
If you want, I think you can paste the code to chat box even.
Sure.
Yeah. There is another question from Brian in the Q&A box. Does your work support properties on nodes? And
it does.
He just says he's very excited.
It does. Although we have not experimented much with the property maps, but currently the Chapel Hypergraph Library does support property graphs.
And questions keep coming from Brian. And he's asking about property maps. H property maps, sorry.
Yes.
Okay.
Yeah. We do support properties both on vertices and edges.
Okay. I had one question that is kind of tangential to your work, and you show some profiling information. I'm kind of curious, what kind of tool have you used to profile Chapel, and what was your experience with it?
That was basically Chapel V's.
Okay.
Yeah, and it was pretty easy actually to work with that.
Okay.
Engin, there was an audience member who had a comment about one of the comparisons. I've just unmuted.
Yeah, hi, this is Emily. Can you hear me?
Yes.
I can, yeah.
Awesome. I just wanted to comment because I was seeing a couple of things in the chat about the comparison that Jesun showed on the CHGL homology versus Julia and C++ homology. And I just wanted to comment that the underlying algorithms between those two are somewhat different. And so just the mathematics behind the computation of homology is somewhat different. So it's possible if we implemented the same algorithm in Chapel as is implemented in C++, we could very well beat it. We don't know. So just the comments that you guys were saying about, you know, we want to beat Julia and C++, it's possible that we could already. It's just the algorithm that's underneath what we're doing is slightly different.
Thanks very much.
All right, thanks. And it's 12:55. Thanks again, Jesun, for the great work and the great talk.
Thank you.
It says most of the CHGL examples, your work examples, seem to stem from test data. I'd like to see full examples from actual data, like perhaps large network graphs.
Definitely. So we were actually targeting active DNS dataset from Georgia Tech, and they're quite big in the sense, and currently we are targeting 1 day worth of data, and we have planned to scale it for more than 1 day. And yeah.
All right, thanks.